Another good suggestion for a video is where we could talk about stereoisomerism for a bit. Right, so this is not to be confused with structural isomerism, which you need to know about too. And I'll verbally say, but not write, that structural isomers are molecules which have the same molecular formula. So, for example, C6H10O or something, but they have different structures. It might be they have different functional groups or different connectivity, or they might have different chains or different side chains, whatever it might be, but they have the same molecular formula but different connectivities. That's how it's kind of worded in the scheme. But we're going to spend some time talking about stereoisomerism, and you're expected to know these are when you have molecules with the same structural formula but different arrangement in space. And I'm going to write it out like that now, and also exactly as it's written in the scheme of work. So the way that I've taught you, and I stand by this, is they would have the same structural formula. So for example, CH3, CHCl, CH2, CH3. That would be an example of a condensed structural formula, or it could be one that's a skeletal structure or a fully displayed structure, but they'd have a different arrangement in space. And by the way, and we'll talk about what that means in a minute, or, as exactly worded from the specification, the same constitution, and by that it means what atoms they are, just like we've got here, what the connectivities are, in other words, what atoms are connected to each other, bond multiplicities, i.e. single, double, triple bonds, but a different spatial arrangement. So it's essentially the same thing as what I've told you. Okay, so stereoisomerism can come in a couple of different forms. So the different forms are cis trans isomerism, which I'll spend a bit of time on to start with, and also optical isomerism. I can't write. Optical. So cis trans isomerism to start with is when, well, there's a couple of situations when you can get cis-trans isomerism. So you can either get it when you've got a small cyclic compound, such as a cyclopropane or a cyclobutane, and we'll look at what that might look like. So if you can imagine this kind of sort of flat, like my hand is this way, that's my attempt at drawing that. If you've got a molecule like that, each carbon will have two groups coming off it. We're going to consider the two carbons nearest to us. Now you can either have the two groups both underneath the ring, like so, in which case they'd be what we call cis, or you can have one of the substituents, it could be chlorines by the way, this, or CH3s, or whatever it is you're interested in. It'll be really clear from the question, or one above and one below, and then it would be trans. And you can do this with 4 and 5 members, well, 3 and 4 you're expected to know about membered rings. So here's what the 4 would look like. That's just a square, but I've drawn it like that to try and make it again look like it's like my hand sort of pointing that way. So you can have a group pointing up and down, that would be trans. So that one's trans, and cis would be like that, with both the CH3s beneath the ring and there'd be a hydrogen above. So it's very similar to this, but with the 4-membered ring. So that's one way of getting cis-trans isomers. And I'll just add again, this could be, for example, CH3 side chains. It could be chlorines as well, whatever. This comes about, and this is the same for when we talk about double bonds, as we'll see in a minute, because the chlorine can't jump from here to here. The methyl here can't jump from below to above. The CH3 can't jump from here to here without breaking another bond. So you can't just rotate the molecule from one to another. If you have, by the way, something like this, which would be simply simply butane, this bond here can rotate because it's a sigma bond. Now, when it's a ring like this, this bond can't rotate because it's being fixed in place by the fact that it's in a circle like this. All right. But you can also get cis-trans isomerism with alkenes. So you'll only be given to look at alkenes where you've got 2 carbons either side of the double bond, of course, making an alkene. But on one carbon there'll be 1 hydrogen and a carbon chain. On the other carbon there'll be a hydrogen and a carbon chain. You can't get cis-trans isomerism if you've got 2 carbon chains on one side or 2 hydrogen chains on one side. The cis-trans nomenclature doesn't work if you've got 2 carbon chains on one of the carbons, and they wouldn't be stereoisomers at all, cis-trans isomers at all, if you had 2 hydrogens there, because if you flip it around you get the same molecule. But these exhibit cis-trans isomerism again because this bond can't rotate. This CH3 can't flip from here up to here, and it can't rotate because you've got a sigma bond between the 2 carbons, which in theory could rotate, but the second bond is of course a pi bond that we'd label like that. That's sigma. These 2 together are the pi bond. You can't rotate this molecule about this bond here without breaking this pi bond. And so you end up with the molecule being fixed in either this place, which is cis, because the 2 CH3s are on the same side, the 2 carbon chains are on the same side, as opposed to where one of the CH3s or carbon chains is above and one of them is below, and that's trans. This could be any length carbon chain, but you're going to have a hydrogen here and a hydrogen here, or a hydrogen here and a hydrogen here. Okay, so that's when you can get cis-trans isomerism as well. And since I'm on the topic of stereoisomers, let's talk about optical isomerism. And this is when you've got a chiral center in a molecule. Okay, so you have to be able to spot and recognize a chiral center. And a chiral center, there are more than one way of getting these, but for the IB you need to know that a chiral center is when you've got a carbon with 4 different groups on it. And you've got to be able to draw these for the exam. So whatever chiral center, whatever molecule you've been asked to draw with a tetrahedral carbon, so sp3 hybridized carbon, sp3 hybridized tetrahedral carbon, you've got 1 bond going up, 1 bond coming down to about 7 o'clock or 8 o'clock on the clock. And the other 2 bonds are going to come out over here somewhere, one just ever so slightly in front. We do that as a wedge coming towards us, and one with a going slightly bit behind. So again, they're both within that. If you try and imagine that as a quadrant, both bonds are within that bottom right quadrant, or wherever you want to draw it. So either bottom right or bottom left quadrant, say. And this will be a chiral carbon if there are 4 different groups coming off it. It could be that 2 of the groups have carbon chains, as long as they're not the same, exactly the same carbon chain. Or it could be that they're completely different atoms, like chlorine and hydrogen. So this molecule would be chiral because it has a chiral center. Sometimes people call those asymmetric centers or stereo centers, and this will therefore exhibit optical isomerism. What that means is, well, first of all, it means it will have a partner molecule, if you like, what we call an enantiomer. So this is be a pair of enantiomers. I'm going to draw enantiomer pair. If you asked to draw the enantiomer pair, the best way I think to draw it is a mirror image of that molecule. So if you can do that, that's the way to go. Failing that, you can just draw the same molecule again exactly as is, but just switch any 2 and only 2 of the 2 groups. That's the other way of drawing it. But so these 2 molecules then, these enantiomers, are what we call non-super imposable mirror images of each other, just like hands are. So my left hand and my right hand are non-superimposable mirror images. They can't, even though they kind of look the same, mirror images of each other, they're not the same. When you do, you can't put one on top of the other and then be the same. Okay, right. So these molecules themselves have no plane of symmetry, it's said as well. There's one or two things you need to know about these types of molecules, these chiral molecules. So one is a kind of physico-chemical property, which is that we can detect when we've got a single enantiomer. I should have said that if you've got a 50-50 mixture, then we call it a racemic mixture. Racemic mixture if you've got 50-50, one enantiomer and the other. But if you've got a mixture where you've got more of one enantiomer than the other, or most likely in an IB exam they talk about having either one enantiomer or the other, what would happen is if you shone plain polarized light through a sample of that solution, or through that liquid, most likely a solution, so you shine plain polarized light through a solution, what will happen is that the plain polarized light will rotate. So don't write PPL in an exam, write plain polarized light, but it will rotate in one direction, and that will be either clockwise or anti-clockwise. So it will literally rotate through as it goes through the thing, and you can detect that. You don't need to know how you detect it. The other enantiomer rotates it in the other direction. It will be anti-clockwise, and it will be rotated for the same concentration solution. It will rotate it exactly the same amount of the other direction, in the other direction, and the racemic mixture will rotate. Well, it will appear like there's no rotation at all. So half the molecules will be rotating it one way, half the other, until you end up with no rotation at all. So racemic mixtures don't rotate. Single enantiomers rotate either one way or the other. You are really expected to know that chiral molecules, there are some very important consequences in biology. So a huge proportion of biological molecules are chiral, with very few exceptions. And chiral molecules will interact with other chiral molecules in a particular way. So for example, a hand, my right hand will only go nicely in a right-handed glove. My right hand won't go in a left-handed glove. And so if you've got, say, a left-handed enzyme or receptor and a right-handed molecule, those two things won't fit into each other, but that enzyme is set up only to interact with one of the two enantiomers. And that has important consequences in biology and medicine and so on. But that's as much as I'm going to say now. I'm sure you'll remember talking about the thalidomide story, and it's probably worth having a reread of that one if you've forgotten it. The other thing to remember is this is useful information when identifying SN1 and SN2 mechanisms. I'm not going to go through all that yet again in this video, but SN1 reactions do end up with scrambling of a chiral center, because the reaction goes via a flat planar sp2 hybridized carbon, carbocation intermediate. What you end up with is getting a 50-50 mixture, racemic mixture of products. If the product happens to be chiral, you get a 50-50 mixture, and so no rotation of PPL. Because if you've got SN2, you get inversion of stereochemistry, you might remember. So you've got a molecule like this one up here, you get inversion of the stereochemistry. The hydroxide would come in from the other side, flipping the molecule a bit like an umbrella, inverting, and you end up with 100% of a single isomer, and you get rotation of PPL, plain polarized light, in either the clockwise or the anti-clockwise direction. It helps you identify whether you've got SN1 or SN2, if you can't otherwise tell. That's a good place to stop. Cheers, bye-bye.